All right. Maybe that'll make it a little better. Okay. We are up to date on grading and whatnot. Homework 5.3 is due today, and I'm giving you homework 5.4. This will be our last column assignment for the semester, is homework 5.4. After that, the rest of the semester, we are in beam land. We're going to be looking at bending. It's going to take a fair amount of time to discuss beams well, because we have sort of two different cases with beam design that we need to consider, and it's all a function of bracing, whether or not beams are continuously braced or discretely braced, because beams, like columns, can have potential to buckle, but they buckle in a little bit of a different way, and how we handle that is just a little bit more complicated. So today what we're going to do is we're going to go back to column design, but the example that we do for column design is going to be much more in-depth than the last one. And the reason is because we're going to find that for this example, the strong axis governs, not the weak axis. And that's going to greatly ramp up what we need to do from a calculation standpoint and what have you. Because for each trial section, they're going to be just that, trial sections. We're not going to know whether or not they work. Unlike the last example, it was just, you could look at it and see that they were going to be sufficient. All right. So let me pull up the notes here. Okay. So we're going to be using a lot of the same references that we used last time. So just make sure that everybody's comfortable with the K values for different interest rate conditions. I think by now we're all pretty comfortable with that. Again, just make sure to use the recommended values and not the theoretical ones. The analysis method, so the two analysis methods that we have available to us are, for one, to just do it the hard way, if you will, which is just to break it out and actually calculate the capacity of the column directly, which is definitely what I think you should do at the very end of a design problem once you've selected a column. And I think that will be very apparent after today, because in order to get to our final answer, it's going to be, there's a little bit more runaround than we did last time. So, we get our governing slenderness, calculate the elastic buckling stress, then use that to calculate the critical buckling stress, and then ultimately our factored capacity. Analysis method 2, which is using table 4-1A, that's really what we're going to be living in a little bit today in order to perform our design. And so remember, the main crux of it is that table 4.1 lists our capacity based on the column buckling about the weak axis. Which, again, I think that's the default way that we should be listing a column's capacity. So the idea is, here's a column, I take a column, I load it in compression. No matter which way I hold it, it's always going to buckle this way, because that's the weak axis. The only time that the strong axis would ever govern is if there's some means of bracing the column. And if there is, then we need to sort of roll up our sleeves a little bit. And that's where we compute our KL effective, and then we linearly interpolate in table 4.1 to get our capacity. Now for design, what we're doing is we're factoring our load, getting the largest KLX and KLY for the column, and then, like last time, we're selecting trial shapes. Okay, selecting a trial W14, a trial W12, a trial W10, and a trial W8. I am using that word trial very carefully, because unlike the last example where it was apparent that the weak axis was going to govern, with that example, if the weak axis governs, they aren't trial shapes. We know they work. But if the strong axis governs or potentially governs, we don't know. We have to check each one. So we're going to select a family of possible column selections, and then for each one of those, we have to check them. Okay? So if KLX is less than or equal to KLY, we just know that from the group, we select the lightest one. But for this problem, that's not going to be the case. And so for each column, we're going to have to check it. And I would argue that of any day where you really want to pay attention and make sure that you see the big picture for what we're doing in our calculations, today's the day, because there's a lot of time that you can save on your calculations, on homework, and on exam problems if you recognize the big picture. And that'll become really clear today. And then finally, again, once you pick a section, make sure you analyze it using method 1 just to verify that the column works. So this is the column that we're going to do today. Okay, let me pull up the notebook. This is going to be our goal for today, is looking at this column. Okay, so what we're going to be doing in this problem is we're going to be selecting the lightest W shape that we can to resist a factored load of 650 kips. So right off the bat, I went ahead, let's go ahead and make that part easy. I think by now we know how to do 1.2 dead plus 1.6 live. So we're designing for 650 kips. So 650,000 pounds is what we're designing this column for. Now I've given you the bracing configuration shown. I also decided, let's go ahead and make that part easy, okay? Because we've already handled example problems and homework problems where the bracing configuration gets weird. Let's just keep that part simple, okay? So we've got a situation where the x-axis is unbraced along its entire length. The y-axis, we have a brace at midspan. The other thing is that everything's pin-pin, so we know that K is 1 for every segment. Again, we're keeping that part easy, okay? So that part's really straightforward, okay? So I'll give everybody a sec to copy all this down, and then we'll get into it. While you're doing that, let's go ahead and, let's go ahead and handle a few design steps. So we know that PU is 650 kips. Again, that was given. And then step 2, we know that our KL about the x-axis is 32 feet. And then our KL for the y-axis is 16 feet. All right. Okay. Some basic stuff. Everybody brought your steel manuals today? You're going to be using them? Okay. So let's see how comfortable we are with this. Okay? So remember, when we look up sections in table 4.1, are we looking up based on KLX or KLY? KLY. Okay. So here's what I want to do. I want to look up some trial shapes. Okay. So I want to make sure that everybody's comfortable with this. So let's do this together. Okay. So step 3, we're going to be looking up trial sections. Okay. So let's start off with the W14. Okay, now I want to find the lightest W14 that we can, so the lightest section that we can find that has a capacity of at least 650 kips under a length of 16 feet. Okay, so what is the lightest W shape that you find? I want to make sure everybody's comfortable with this.
Is it 82?
The W14 by 82. Do I have a second on that? Okay, all right. Now, before we move past the W14 by 82, we're going to look up some stuff. Okay? First off, Mr. McDaniel, you looked at that up based on a capacity of what? What was the capacity there?
697.
697 kips. Okay? Now, the other thing I want, we didn't ask this last time because last time we knew that the weak axis governed. These are all going to be trial shapes, so we're going to have to do this for all of them. So help me out. What is Rx over Ry for that section?
2.44.
2.44. Everybody else see that? Okay. Okay. All right. So that's good there. Okay. Now, that is a possible option for this column. Okay. Now let's look up another one. Let's do the W12. Okay. And while you all are looking that up, I'm going to list this here as an option. So option 1 is a W by 82. W14 by 82. We'll list that. That's a potential optional shape. Okay. So let's find another one. So for the W12, so what's an optional W12 that we could use for this problem?
72.
The 72. Okay, do I have a second on that?
Yeah.
Okay. So W12 by 72. What's the capacity?
709.
709. And the RX over RY ratio?
1.75.
1.75. And this is, again, another one of those places where when you're looking at column land and looking at beam land, efficiency doesn't really matter all that much. I would argue from a load over resistance standpoint, this is less efficient, but I would still probably use it because it's lighter, right? So, again, we're sort of throwing that out the window a little bit. All right? W10. Somebody give me a W10 that works.
77.
77. Okay, do I have a second on that? All right, its VPN is what?
686.
686. And its RX over RY ratio is what?
1.73.
1.73. Now, what about W8s? What's that?
I said W8 by 80.
But, well, now hold on, is there one?
No.
No, there isn't one. This is something I was mentioning earlier, that it is possible that when you're looking at trial shapes, there aren't any. Because the heaviest W8s are tiny. I mean, we're talking about a column that needs to hold up 650,000 pounds. And I'm asking, are there any I shapes that are about this deep that can hold it up? No, there aren't. That's a lot of load. That's okay. So it's just recognizing that no W8s are applicable. So I don't want you to, the point I'm making is I don't want you to think if you're in a homework situation or on an exam that this is a problem. It's not. There's nothing wrong with that. Okay? Everybody okay with that? Okay. All right. Now, here are our three options. Okay? Now, before we start checking these, I want to address something right now. Because, to be clear, it's very possible that what you might be thinking is, why don't we just start with the lightest one? And if this one works, then why check these two, because that's the lightest answer. And if you ask me, is that a sufficient way of doing the problem? Absolutely. I have no problem with that whatsoever. Okay? However, for the purposes of this example, I want to go through all of them. The reason I want to go through all of them is that for each of these different options, we're going to reach some different conclusions, and I kind of want you to see them, okay? Because if you go through this process and you see them, you'll understand what I mean when I say that if you're doing this on a homework or on an exam problem, you can do it a lot faster if you see these patterns, okay? So we're going to do all the options, and that's why. So bear with me for a little bit, okay? So let's take each of these trial sections one at a time, and let's assess whether or not they work, okay? So let's start off with, so this step is verifying capacity. Okay, so let's start off with the W14 by 82, okay? Okay? Now, before we get into this, help me out. What was KLY? What was that again?
16.
16 feet. Okay. KLY is 16 feet. Now, in order to check, so what we're doing here is checking the strong axis. In order to check the strong axis, what I need to do for the W14 by 82 is I need to compute KL effective. And the way that I do that is I take KL about the x-axis and I divide it by that ratio. Okay, so what is that? It's 32 feet divided by, what was the ratio? 2.44. And what do I get when I do that?
13.1.
13.11, I think it is. 11 feet. Okay. So what do I do with that 13.11? What's that? Well, no, not yet. That's if we were using step or method 1. Now that I have, well, let me ask you this. Can I look up a capacity for 13.11 feet? No. I can look up a capacity for 13 feet and 14 feet, can I? Okay, so let's do that. Just for the sake of discussion. So what is BPN at KL is 13 feet, and what is BPN at KL at 14 feet? So help me out with that. What is BPN at KL at 13 feet for this section? Again, we're looking at the W14 by 82.
Is 809.
809?
Yeah. And for 14 foot is 772.
Okay. Now I want everybody to write this down. And once you get to the point where you've gotten it done writing, or have finished writing, I want you to look up here. I'm going to ask you a simple question. Normally, we would take these and linearly interpolate. Do we need to do that? You're saying no. Why?
It's both values are greater than the capacity.
Both values are bigger than this, right? It doesn't matter what we get when we linearly interpolate between 809 and 772. It has no bearing, because I don't care what you get, it's bigger than 650, right? So I'm going to ask a generic question. Is this a viable option for our column? Yes. So I will say trial section 1 is adequate. Does everybody see that? Because it doesn't matter, again, it doesn't matter what we interpolate between these two, it doesn't matter. Whatever we get, even if it was 772, 772 is bigger than 650. In fact, I'll go you one further. For this column, KLY was 16 feet. What was KL effective? What was it, 13.11 feet? Looking at just these numbers, I didn't even need to look this up. Because by recognizing that KL effective is 13.11 feet and KLY is 16 feet, I know that the capacity of this column is based on the weak axis, not the strong axis, and the actual capacity of the column is 697 kips. Does that make sense? The point I'm getting at is I'm trying to save you from having to linearly interpolate every step when you didn't need to. Does that make sense? Yes.
Does this also relate to my question on Wednesday when I was asking why not just start with KL effective? Like,
Yes. And I want to go back to that after the next two. Because the next two, I think you'll get a bigger picture. All right. So far, so good? All right. Now, like I said, we could theoretically have started with the lightest section, but again, I want to do all of these trial options because with each one, we're going to get a different view, if you were. So let's look at the next one. Let's look at the W12 by 72. Okay, so for the W12 by 72, we need to compute the KL effective. So that's KL X over Rx over Ry. So that's 32 feet over, and what was the ratio for that shape? 1.75. And so what do we get for this? 18.28. Do I have a second? All right. Do I have a second?
2.9.
Two.
Budget.
Oh. We have some contention here. 18.28, 18.29. Again, we're getting tense in here. Again, Marshall University policy says I'm allowed 7 mistakes per semester, but again, I'm the one tracking the mistakes, so I know it's a corrupt system. I'm a dork. All right, so, okay. So, just like last time, we should probably look up a capacity between 18 feet and 19 feet. So, let's see what we get. Also, for this column, does the weak axis govern or does the strong axis govern for this column? What's KLY? But yeah, it's
Yes.
KLY is 16 feet. What's KL effective? 18 feet. So does the weak axis govern for this column or does the strong axis govern for this column? Strong axis, because this is bigger. This is indicative of a more slender segment. So what are we getting for these capacities here?
656 and 629.
All right? Let me ask you a question. Is there value in linearly interpolating this one?
Yes.
Yes, because we're somewhere between 656 and 629. What do we have to have a capacity of? 650. So, yes, we do need to linearly interpolate this, right? So, what do we got? All right, so we've got x1, y1, x2, y2, and x. So x is 18.29. This is 18, that's 19. This is 656. This is 629, and we are using linear interpolation, right? So, what do we get here? All right, so what do we get when we handle this? So it's y equals y1 plus y2 minus y1, x2 minus x1 times x minus x1. What do we get when we check this out?
648.
648.2? So therefore, VPN at a KL of 18.29 feet is what? 648.2? So, is this section adequate or not? No, it's not. It doesn't have enough capacity. This column is going to be governed by its strong axis capacity, not its weak axis capacity. And this is definitely a place where checking that strong axis capacity is very important. I mean, we looked this column up. Table 4.1 said it had enough capacity, but again, Table 4.1 is assuming the weak axis governs. If you check the strong axis, you find, I don't know, actually the strong axis governs and it's not good enough. So, therefore, trial section 2 is inadequate. So, if I look at my options here, this one's good. This one is not good. So, now let me ask you a question. Is there any value in even checking the W10 by 77? Well, yeah, because if it works, it's gonna be lighter than the W14 by 82. The W14 by 82, that's 82 pounds per foot. This is less. Less weight per foot means less hit on our wallets when we have to buy that shit. So let's check the W10 by 77. So again, 32 feet divided by, what was the ratio for this one? 1.73. What do we get for that?
18.5.
18.5. That's a nice value for interpolation, right? Because we can just average them, right? But let's see what we get. So if we're at 18 and a half feet, we need to look up 18 feet and 19 feet. So what do we get for 18 feet and 19 feet?
617 and 587.
587?
582.
582. Sorry, can't read my handwriting.
That's okay. No worries. Now, let's take a step back. Is there any point in doing the linear interpolation? No. Why?
Both those are lower than the required.
Yeah, both of those are less than the amount of load that the capacity needs to be. So it doesn't matter, right? This column is inadequate.
How do you feel about, for the second one, eyeballing the interpolation? Because if that upper value is so close to 650, if you know it's going to be, because it's only 18.3,
Yeah, if so.
shade so much closer to the lower one that you wouldn't even really need to do it.
Well, so here's what I would say. So 18.3 is kind of close enough that I feel like I probably need to do it. If it was 18.9, I wouldn't bother.
Okay.
If it was 18.03, I probably wouldn't bother. But it's kind of like right there, and I can't see it. That's just me. I feel like it was necessary. But again, as long as you can justify your calcs, that's fine. Okay, but this one's inadequate, right? We know this one's inadequate. So here were our three options, right? Pretty easy choice, right? This one worked, these two didn't. That's our answer. Now, I still think we should analyze that using method one, but, and I'm gonna do that here in a second, but does everybody kind of see sort of the option here? If you have multiple options that work, pick the lightest. Now, and a common question that I might get here is, well, wait a minute, Dr. Mike, what if none of them work? What if none of these work? Go back to table 4.1, pick the next heaviest W14, the next heaviest W12, the next heaviest W10, do the process again. And keep doing it until you get a section that works. Now, the only time that you would probably need to do that is when there is a really big difference between KLX and KLY. Like our KLY is 16 feet and our KLX was 32. If it was 16 and 48, we might have to do that a couple times. So now now that we've gone through that, let me go back to your initial question. What was your question about?
So why would you not go straight to KL effective and just use that in the design aid?
Okay, the reason why is because every shape has a different RX over RY ratio. So how do you compute a general KL effective?
Yes, you could.
That's what I'm saying. So, like, if you just look at the three trial shapes that we picked, right? The three trial shapes had anywhere from 2.44 to 1.75, 1.73. Who knows what they are? It's really difficult to predict an RX over RY ratio at the start of design. Now, there are groups of them that have common values, but there can be a little bit of a range there, especially as you start getting into much heavier sections, okay? So, I don't really think there's a better way of getting the lightest shape every time, is really sort of what I'm getting at.
But so probably it looks like a W12 by 79 probably would work.
Okay, I was gonna get to that.
Because it's the same R value as but it has higher capacities.
I was gonna get to that, so that was gonna be the last thing that I said, is that you can go back to the table and say, well, what about a W12 by 79? I'm not gonna make you all do that, but it is a possibility. I won't make you do that, so, but it's possible. So, if you look at the W12 by 79, what is the RX over RY ratio for that?
1.75.
1.75, and so between 18 and 19, you're at 723 versus 694, so that one probably could have worked as well. I'm not gonna make you do that for the purposes of this, but it is an option that you could have checked. So. But one thing I do want you to do, here's one thing I do want you to do. In the middle of a homework problem or an exam problem, you've done all this linear interpolation, I do think it's valuable to go back and analyze the W14 by 82. I really think that's valuable, okay? Because, again, especially what if this section worked? What if this W12 by 72 worked? If that W12 by 72 worked, we would have been assuming that it worked based on an interpolated capacity. I think it's worth it to go back and check and make sure that it works. So, in order to analyze this section, we're going to need the RX and the RY independently for the W14 by 82. We know that KLX is 32 feet. We know that the KLY is 16 feet. We also need the AG. All right. Now, at the bottom of table 4.1, you can look up the AG and at least the RX, but you're going to need to go to table 1.1 to get the RY. So help me out. What are these properties? I need the radii gyration in the area.
First area is 24.
24 square inches. And RX and RY.
6.05.
6.05. 2.48. All right. So the first thing that we're going to have to do is compute the KL over R for the x-axis. So that's going to be 32 feet over 6.05 inches. But again, we're going to have to convert that. And then KL over R for the y-axis, 16 feet over 2.48 inches times 12 inches per foot. So what do we get for this? What? For the, did you multiply by 12?
All I did so far.
Ah,
63.47.
so 63.47 and then 77, I think, 0.42?
Yep.
So from these, what I'll do is take the largest, right? The largest one that governs. And here's something that's kind of interesting. What is this saying if KL over R and the y-axis is what governs? It's saying that weak axis buckling governs this column, right? That's exactly what we found earlier, right? This is just more or less verifying that what we did is correct. Because when we did the W14 by 82, we got this and we found that there was no need to interpolate because it didn't matter what we got. We knew the section was going to be adequate. We're going to see the same thing here. But again, I still think this step is valuable when you've gone through back and forth a few different trial shapes. So, we're going to compute our elastic buckling stress, so pi squared times 29,000 KSI over, and then we'll use our maximum slenderness. Remember, slenderness has no units.
I got 47.7.
47.75 KSI. Do I have a second?
Yeah.
All right. All right. Next thing we need to do is we need to compute F critical, but in order to compute F critical, we have to compare our KL over R. With our limit that tells us whether or not we're in inelastic or elastic buckling. This is the stuff that we did last week. I'll say something. This part right here, if we're always using 50 KSI, then this calculation is always going to yield the same answer. And so if it's always going to yield the same answer, this is a great addition to a formula sheet. Like for 50 KSI, 4.71 times the square root of 29,000 over 50 is 113. So just put that on your formula sheet so you don't have to keep redoing it. I think it's 114.4, but that's close enough. So this tells us then this is the expression that we're going to use. Again, this is the same stuff we did last week. Remember, again, this is an exponent. So and so what do we get for that?
I got 32.26.
Say it again.
32.26.
32.26, so I have a second.
Yep.
All right, and then so what do we get for our capacity? If I'm guessing, it should be something like 649. Or sorry, no, 697.
696.82. Close. You're close.
So yeah. So again, I think you'll find that the process is very similar. And again, to go back to Mr. Odell's question, every now and then it's possible that you might have, like for example, another W10 that's lighter than the adjacent W12. That doesn't happen really all that often, and I'm not going to make you worry about that on homework or an exam, so I'm not really all that concerned about it. It's possible, but I'm not worried about it. And if so, if it does happen, you're only talking about a couple pounds of steel. It's really not too big of a deal. So, let me. What I'm genuinely most interested in is your understanding of the process, and more importantly, like when to be able to critically look at the data that's been provided and to know when you need to interpolate and when you don't need to interpolate. That part I'm most interested in because it will take what seems like a really, really long problem and make it really short. Because I know this seems like a lot of work, but it seems like a lot of work because we've been going through it step by step here. My question to you is, if I give you another column design problem to do at home, can you take what was probably 2 to 3 pages of work and turn it into 1 page of work because there's a lot of stuff you didn't need to do? That's my question for you. Does that make sense? Again, if you wanted, you could be systematic like what we did for this section and just do that for all of them. I think that's probably more labor intensive than it needs to be. Yeah. Any questions? What time is it? Am I letting you out a little early? I'm letting you out, I think, 8 minutes early. If you're okay with that, if you want, you can stay. Okay. All right. What we're going to do next time, just so everybody's aware, this is our last lecture on columns. Again, as I mentioned earlier, and what we're going to be doing next time for the rest of the semester is focused on beams. So remember those shear and moment diagrams you did in structural analysis? Guess what? Guess what? They're coming back. All right. That's all I got, everybody. I'll pull the code up again, but I will see you all next time.